In this next section, we're going to discuss the ozone.
Oxygen atoms in the atmosphere are almost always found in pairs as part of this diatomic molecule, O2. However, it can also be found in an ozone molecule, which is composed of 3 oxygen atoms, O3. Ozone is formed in the lower atmosphere by the interaction of sunlight and volatile hydrocarbons released from man-made sources like cars, power plants, and other things, and natural sources like sunlight and lightning.
Ozone is dangerous to breathe and is in its highest concentration near major cities in the summer. It is a major component of harmful air pollution. In the lower atmosphere, ozone is a pollutant that is a component of urban smog. Ozone is also formed in the upper atmosphere, the stratosphere. Ozone in the upper atmosphere is not a hazard since it is not breathed, and there it provides a major benefit. It absorbs harmful, high-energy ultraviolet UVB light. It protects life on the surface of Earth from that dangerous radiation. The ozone layer lies in the bottom part of the stratosphere. You can see it here. If this is the stratosphere, this dotted line of the ozone layer is the bottom part of the stratosphere. About 90% of all the ozone in the atmosphere is located in that layer. The ozone layer plays a critical role in protecting life on Earth by shielding it from UVB radiation. Ultraviolet radiation is composed of 3 components: UVA, UVB, and UVC. The highest energy and most damaging to life being UVC, and the least damaging being UVA. Some amount of UV light is beneficial, as it helps produce vitamin D. But UV light can also cause burns and genetic damage that can lead to skin cancer, so too much exposure to UV light is considered harmful. The body reacts to exposure to UVB light by creating melanin to help absorb that light at the skin's surface, rather than letting it penetrate and do damage. That is the process by which people, quote unquote, tan through exposure to sunlight. That process takes 2 or 3 days, since it takes time to produce the melanin. The risk of damage from UV light is partially reduced by oxygen and nitrogen in the air because they absorb most of the sun's UVC radiation before it can reach Earth's surface. But they do little to reduce UVB or UVA radiation. UVB radiation is dramatically reduced by the ozone layer. UVA radiation is not reduced much in the atmosphere and mostly reaches the surface of the Earth. While considered the least dangerous of the UV light, it is becoming clearer that overexposure to UVA can also be dangerous. To prevent damage from the sun's rays, precautions against overexposure to sunlight should always be taken. This NASA illustration shows the absorption of the 3 forms of UV radiation in the atmosphere. The combination of oxygen, nitrogen, and ozone prevent UVC from reaching Earth's surface. So that happens here. Ozone is primarily responsible for absorbing UVB, which you see here, although some does reach the surface. The UVB radiation that reaches the surface is primarily responsible for sunburn. Most of the sun's UVA radiation reaches Earth's surface. Caution needs to be taken to avoid overexposure to UVA and UVB. Let's discuss now chlorofluorocarbons and their impact on the ozone layer. Chlorofluorocarbons, or CFCs, were developed in the 1940s and were in widespread use by the 1970s. They were used as refrigerants and propellants in aerosol spray cans. They were inert and considered safe, and in the troposphere where we live, that was the case. However, in the 1970s, it became clear that CFCs were accumulating in the atmosphere and reaching the stratosphere. There, UV light could break them down, and the chlorine atoms could react with ozone. Studies showed that those reactions were leading to the rapid decline of ozone in the ozone layer. This was clearly a danger to living organisms, including people. The use of CFCs in refrigeration, one of the trade names was Freon, was considered vital, and efforts to ban or limit their use met with great opposition. But growing evidence led to action. By 1985, it was documented that ozone over Antarctica had been reduced up to 40%, and that depletion was spreading as a hole in the ozone layer that would soon affect human populations. In 1987, 56 countries signed the Montreal Protocol to cut the use of CFCs by half. In later years, it was agreed to phase them out altogether. During that time, replacements were found for CFCs, so concern over the economic impact was overcome. Due to the long life of CFCs in the atmosphere, they are still affecting the ozone layer today, but the impact of the treaty to ban CFCs is well documented. This map from NASA shows the hole in the ozone layer, this light blue part over Antarctica, in June of 2021. While the hole is still present, it is of much lower concern than it would have been without the implementation of the Montreal Protocol. It is hoped and expected that by maintaining that protocol, the CFCs will eventually be consumed and the ozone layer will fully recover. This video provides an overview of the current state of the ozone layer, the fact that it will still be many years before the effect of CFCs is overcome, and the benefit of the global treaty to ban the use of CFCs. We aren't going to watch the video now, but feel free to click on the screen here that will take you to an approximately 3-minute video to discuss this.